If you sit on that side of the room or up to about here, it's much better because then I will be able to spot if you raise your hand and have a question, right? I'll be sitting right here and then I can see the room. I'm going to be monitoring both the Zoom questions and the questions in the room. When you have a question in the room, we've got 2 microphones here. I'm going to give one to you so that you can spread it maybe around, quickly get it to the person on this side of the room, and I'll give one to you so that we can quickly get it here. Just raise your hand and I'll call on you, and then there are also microphones in the ceiling, so we should be able to pick up the sound relatively well for the call. So please, despite this sort of format, ask questions. I think that's what this is for. Okay, without further ado, welcome. We talked on the first day about causal graphs, on the second day about about causal discovery, and so at least part of what Thomas is going to be talking about today is about a somewhat different language of looking at causality, namely in terms of potential outcomes. And I'm very glad that Thomas was willing to do this. He's professor of statistics at the University of Washington. Thank you, Thomas, for doing it. The floor is yours.
Great, thank you. So yeah, let me post, there was a request for slides. So I'm going to post the link for the slides into the chat. So just give me one moment to do that. So here we go. And I'm also going to, let me just check I can do that. Okay, so here's the link for the slides. And I will also make use of a whiteboard. Here is the link for the whiteboard. Okay, so yeah, so I was asked to say a couple of remarks about sort of at a high level, and essentially at a high level, I think all causal models are trying to link 2 things together. They're trying to link together a world in which we perform an intervention of some kind and a world where we observe a system without performing intervention. Spencer's talk on the first day introduced causal models in a way that's very natural from a graphical perspective, where we start off with a DAG describing the system in the absence of interventions, and then we by removing edges, come up with another graph describing the system after we intervene. Potential outcomes, in some ways, you can think about them sort of go the other way around. They start by thinking about distributions resulting from interventions, and then work back to what we observe in the absence of intervention. But I'll try to make this clearer both in this lecture and also in the first lecture this afternoon. So what I'm going to talk about in the next hour is I'm going to give you a brief history of causation, talk about potential outcomes and counterfactuals. So in the philosophical literature and also some statisticians make a big distinction between the potential outcomes and counterfactuals. I'm going to use them synonymously here. It's not simply because although there are interesting distinctions to be made there, I don't think they're relevant to most of the points that I'm making here. I'll then talk about randomized experiments, average causal effects, and observational studies. So people have been interested in causal relationships for a long time. This is the sort of quote from Democritus, basically saying he'd rather find a single causal relationship than the king of Persia. We then jump forwards to Hume in his inquiry concerning human understanding. He says, we may define a cause to be an object followed by another, where all the objects similar to the first are followed by objects similar to the second. So sort of in modern terminology, he's essentially saying that if there's a cause, we would expect there to be some sort of association. But then obviously, you know, there's an issue that immediately arises with that, which is that, well, we can think of situations where there's an association, but we wouldn't think of it as being causal. And so he adds this condition saying, where if the first object had not been, the second never had existed. So notice that I'm writing this here to indicate he's now not telling you about what he actually saw, or what we would necessarily see, but he's telling us about what we would have seen had things been different. I also just add to the philosophers there, who may already know this, that Hume is sort of famous in philosophy for 3 different causal theories, but this isn't one of them, essentially, although David Lewis, I think, is responsible for sort of popularizing this particular bit. Okay, so now we jump forwards to the start of the 20th century, and people are doing agricultural field trials where they want to know which seed varieties produce or cause the greatest yield, or it could also be which fertilizers produce the greatest yield. And there's an immediate problem that arises, which is that the plots of land that these different seeds or varieties of seed are being tried on are not all the same. Some of them, may have more rocks buried in them. Some may have better drainage. All kinds of things may be going on. And so there's a sort of realization that it's not possible to hold all of the conditions constant. And so Neyman spent a lot of time at Berkeley, but this is before he spent time at Berkeley. This is his master's thesis in 1923. He came up with this conceptual framework, which in some ways, if we can think of as sort of formalizing what Hume was alluding to, where he says, supposing that we're interested in comparing V varieties, so those could be seeds, for example, on M plots, then we will consider a set of numbers, a matrix like this, where Uij is the crop yield that would be observed if variety I were planted in plot J. Okay, so the key point is, so each one of these this little picture over here, each one of these sort of strips, we can only plant one crop in each strip. In general, we can only plant one crop in each strip because then, even if we were to plant a different crop there the next year, the weather conditions are not going to be exactly the same, and the condition of the soil is not going to be exactly the same, and so on. So the key restriction here is that each plot can only have one variety planted in it. But conceptually, we can think about this set of numbers. So here, the first column of numbers here, this first number is the number that we will observe if we decide to plant variety 1 in strip 1. The bottom number here is the number that we will observe if we decide to plant variety V in strip 1. But we will only get to see one number in that column. Okay, so that's a physical constraint. So we're only going to see one number per column. And so now essentially what we have is we have a missing data problem. We have this matrix that conceptually exists, but we are only going to be able to see one number from each column. Okay, so now just to take it forwards and think about a medical example, and also to simplify it a little bit, we're going to think about, we could think about a randomized controlled trial with a treatment or drug and a control or placebo, and I'm going to use X to indicate treatment or control. And for each patient, we're then going to observe an outcome, Y, which will either be good, e.g. recover, or bad, die. And just to keep things simple to start with, I'll just think about that as being a binary outcome. So binary treatment, binary response. So we've switched from plots in a field to patients and kilograms of wheat. Instead of that being our response, we've now got live or die as our response. Okay, and so we've now got two random variables that we can think about defined for each patient. Y of X equals 0 is the value of Y, the outcome that would be observed for that patient if they were assigned to X equals 0. And Y of X equals 1 is the value of Y that would be observed for a given unit if assigned to X equals 1. And so we're writing, so these are two separate random variables. So to those of you that are sort of deeply into probability, you might be thinking of these as sort of realizations, and somehow this is, like omega. So don't think about it like this. Think of this as just two different random variables defined on the same underlying sample space. So for each patient in our population, conceptually, there are two numbers associated with that patient: the outcome that they would have if they were in the control arm, and the outcome that they would have if they were in the treatment arm. Okay, and also this equal sign takes up a certain amount of space, and we're going so for notational reasons, I'm often going to shorten y of x equals 0 to be y of x sub I. So that's a shorthand for this. So this model was due to Neyman back in the 1920s, but it was popularized by Rubin in the 1970s. And so it's sometimes called the Neyman-Rubin causal model, or even just the Rubin causal model. So I should also let you know, if you read in this literature, other authors use slightly different notation. So there are other authors that will write this as y super x equals I, or y subscript x equals I. Okay, so this is where we've got to at this point. We have conceptually this model. Here is a very simple little conceptual data set. I've got 5 patients, and each patient's got their outcome under control and their outcome under treatment. Okay. And then the way that the data that we actually observe gets generated is in a very natural way. We go through and we decide for each one of our patients whether or not they're going to get treatment or control. So that gives us this column here. And then the observed data, the outcomes that we actually get to see, are then just given by essentially copying across the entry from the relevant potential outcome set of potential outcomes. So here, the first patient was assigned to treatment, so then the outcome we observe for them will be this number. Second patient is assigned to control, so the outcome we observe for them will be this number here, and so on. Okay. So notice here, the thing that comes first are these potential outcomes, and then the observed data is generated from them in this sort of stepwise fashion. Okay. And so there's this property. This could be expressed. What I've just shown you in that table could also be expressed by this sort of simple formula that just says that our observed outcome is equal to y of x equals 0 if x is 0, and is equal to y of x equals 1 if x is 1. Or equivalently, we could also write it like this, that if x is equal to little x, then y is equal to y of little x.
Thomas, quick clarification question in the Zoom. So in the potential outcome framework, the random variable for the treatment and control is indexed for a particular individual?
So yeah, so basically for each individual, they have 2 outcomes conceptually. We're only ever going to get to see 1, but for each individual, it's a bivariate distribution. So they conceptually will have both outcomes. Does that answer your question?
Yes, let's move on. Yeah, it's a Zoom question, so.
Yeah, I saw. Okay, great. Yeah, so sort of we have this is a little bit tautologous. For an individual who has x equals little x, their observed response y is equal to the response y of x that would be observed had x been x. Right? This is a bit unnatural because of the way that we usually when we think of subjunctives, that they aren't things that actually happen. But this is the meaning of this consistency. Okay, and so then we can think about, in the simplest case where y is a binary outcome, we can think of a patient as belonging to one of 4 types. If both of their entries are 0, they're of type never recover. If their outcome under control is bad, but their outcome under treatment is good, then they're helped, and so on. And although I should note here that, again, language is a little bit problematic here, that although this helped and hurt has a kind of, and also never and always has a temporal connotation, but here we're really thinking across possible worlds. So someone who's helped, we mean they're helped in the sense that if they get treatment, their outcome is better than it would have been had they got control.
Speak up. Just speak up.
Okay, it's like Oprah style.
Okay.
Okay. No, but seriously, I've always been confused about this. Like, are you postulating basically a typology of intrinsic propensities of units, like that this to be the type of unit that is denominated by never recover is just to be defined by intrinsic causal propensities, which is you don't respond to the drug, and then so on and so forth. So the idea is that these people are of certain types. So yes, there is some ontology that's going on here. We are supposing that each person is of one of these 4 types.
Okay, so essentially, it is to say that we're only giving the person treatment at one point in time, and we're seeing one response, but we are so somebody who's never recover, it means that in the possible world where they get given treatment, they will not recover, and in the possible world where they get given control, they will not recover. So we are positing that each one of these individuals has these two types. There are people who will take issue with that, who'll say, well, I don't really, I'm willing to think that there is an observed outcome when I give the person whatever I give them, but I'm not really willing to think that there's a single value that corresponds to what would have happened to them had they been in the other arm, because there are too many uncertainties and different ways that their treatment could have been given. And ultimately, as we know, there are lots of philosophical questions about whether or not counterfactual statements are well defined, or whether they are, whether it's meaningful. But on the other hand, I think from the perspective of somebody carrying out a randomized controlled trial, the reason that this is an appealing way of thinking about it is there's this moment in time where they flip the coin, and if it comes up with saying heads, saying you get treatment, then there's the world that occurs downstream from there, and then if it comes up tails and they get control, there's another well-defined world there. So essentially, so the issues about whether counterfactuals well-defined are well taken, but this is a conceptual model. I mean, whenever we invoke a probability distribution, there's a conceptual model that we are invoking. So I don't know whether that addresses your question.
I'm sorry, actually it doesn't. I don't mean to be annoying, but I'm not sure if I understand the answer. Are you saying that we are just positing that there is some distribution of intrinsic types, and by intrinsic types I mean they're defined by virtue of causal properties vis-a-vis the treatment? So there's just some portion of people in the population that will never recover. There's some portion of people in the population that are susceptible to the drug, and there's some people in the population that are lucky that will always recover.
Yes.
Okay, cool. Sorry, thank you.
Okay, maybe I should have said that first. Okay, so the key point here is that the distinction in actual and potential outcomes. So just to add a note here, I think the word propensity there, propensity is an overloaded term, and so that was why, that was why I didn't just say yes to your question.
Yeah,
okay. So the key distinction here is X is the treatment that a given patient gets, and thus far I haven't said anything about whether it's randomly assigned, could result from doctor or patient choices. Y is the observed response for a given patient, and then Y of X is the response that would be observed for a given patient if, possibly counter to fact, they received X equals X. Okay, these are our basic objects. Fundamental problem of causal inference is that we only get to see each person under one treatment regime. So this is going to be our observed data. We're not going to see the entries that don't get copied across. So, this first person, we gave them treatment and they had a good outcome. So therefore, we know that they are either helped or they're of type always recover. But we're not going to know this this question mark, so we're not able to pin down exactly which type they are. But for each person in this simple setting, we all know that there are one of two types. Okay. Okay, and so so it might seem that we haven't made any assumptions at this point, but that's not quite right, because essentially we are implicitly assuming that these are well defined, and there are circumstances we can think of very quickly where that wouldn't necessarily make sense. So, for example, one possibility is, well, maybe there's actually unbeknownst to us, there were two different versions of the drug, and so person's potential outcome would depend on which version they got given. But a more interesting example that's also very relevant to our current situation is that we're supposing that a patient's outcome only depends on whether they're treated or not. but you can imagine if the treatment is being given a vaccine, then whether or not your outcome may not depend just on whether or not you're vaccinated, but also whether or not the people that you are coming into contact with are vaccinated. So, and that's a circumstance where there will be what's called interference between the units, and so these potential outcomes would not be well defined. Okay. Yes, that's what that's saying. Okay, so we can now talk about an average causal effect. So the average causal effect we define as the difference between the expected outcome that would arise if everyone in the population were to be given treatment, and the outcome if everyone in the population were to be given control. So this, you can also think about this as the difference between the proportion of, in our simple setting here, where with binary treatment and outcome, this is the difference between the proportion of people in the population who are helped and the proportion of people in the population who are hurt. So that's going to be, that quantity is going to take values between -1 and 1. Okay, so this is relevant. You can think about this as being relevant to a policy question because it's a difference in the proportion of people that would recover if we decide to treat everyone versus if we decide to treat nobody. A point that I'm going to come back to later is that if the average causal effect is 0, so one way that that could happen is that the drug does nothing and there's nobody who's helped and there's nobody who's hurt, so that everyone's individual causal effect is 0. But it could also happen that, in fact, there are some people that are helped and there are some people that are hurt, but those two proportions are equal. And so the average causal effect is 0, even though for some individuals, the drug is having an effect on them. Okay, so if X is assigned randomly, then so it will follow that X would be independent of Y of X0 and X will be independent of Y of X1. And that will then mean that this quantity, so if this is the proportion of people that have 1, if everyone were to receive X equals I, will be the same as the proportion of people that would have 1 if X was equal to Y among the people who actually get X equals I. This is just here we're using the independence to get this. And then we can go from here to here by consistency. Right? This is simply saying that this is saying that this holds because among people who actually get X equals I, their observed outcome is equal to the outcome they would have had X been equal to I. And so consequently, the average causal effect is then going to be identified as just the difference between the mean outcome in the treatment arm and the mean outcome in the control arm. This identifies our average causal effect. So, so what we've seen is that if these two independencies hold, then our average causal effect is identified from the conditional distribution of Y given X. Okay, so now I want to think about this a little bit more. I'm going to use the potential outcomes a little bit more in order to think harder about this. So under randomization, the relationship between the counterfactual distributions and the observed distributions is given like this, right? So essentially, as we saw, probability Y equals 0 given X equals 1 is equal to probability Y of X equals 1 equals 0. That was the result we had on this. If I stick I equals 0, it's just saying this is equal to this under randomization. Okay, so this is observed. This is the marginal distribution of our joint distribution over those two potential outcomes. Okay, so here are underlying, this is the distribution that I think was being asked about in that previous question. We're supposing that there are 4 types of people in the population: hurt, helped, never recover, always recover. And then, in this is in the control arm, we're going to see the proportion of people that recover in the control arm will be equal to the sum of the proportion of people of type always recover plus the proportion of people of type hurt. The proportion of people that recover have a good outcome in the treatment arm, that's equal to the proportion of people of type help plus the proportion of people of type always recover. So we could think about this, we could say, okay, so if we do a very large experiment, we're going to get to know these two margins with arbitrary accuracy. We'll get to know these quantities. I'm going to talk about statistical inference a little bit later, but for now, let's just suppose we have a very big experiment, so we get to see these, we get to know these margins. What could we then say about these internal cells? So here, I've just written the same 2x2 table in two different ways. This is just using this notation, never recover, hurt, helped, always recover. This is, so never recover, remember, just corresponds to this, and so on. So you could ask the question, given these margins, which is what I get to observe, what could I work out about these internal cells? Okay, so we'd like to know what we can work out about this, given that we get to see this, and given that under randomization, we have these, we get to know the margins from this table. We have these two equations linking what we see in the control arm, what we see in the treatment arm, linking it to these proportions. Okay, so if we think about this mathematically, we can now think about, well, what is this? This is a distribution over these four types. We had the four types, help, hurt, always recover, never recover. That's just four numbers that sum to 1. Okay, and we could think, well, what does a set of four numbers that sum to 1 proportions, what does that look like? So we can think about that as, okay, so just as a, you know, if I had, let's just warm up here. If I had two numbers, say I have two numbers A and B, is my writing visible there? I need to make it bigger. If I have two numbers A and B, actually, no, not possible to go to full screen, but maybe I can make this a little bigger. Yeah, there is another link to the whiteboard. Okay, so if I had supposing I have two numbers A and B, and I have A plus B is equal to 1, and 0 less than A, B less than 1, right? Then if I was asked to display what does this set look like, right? It would look like this, right? That's the set that I would have. And if I went on and I said, okay, now supposing I've got A, B, and C, right? And I'm just doing the same thing, but now let's just write it like this, A, B, C. Right, then right, I can write it like this, A, B, C. It's going to be a little triangle. It's going to be this set here. Okay. That's going to be the set of points that satisfy that. But now we're going to take it up. We're going to take it up one step further. We're going to think about four numbers: helped, is percentage helped, hurt, always recover, and never recover. And I'm going to use the same labeling of the axes consistently through the rest of the lecture. This is going to be helped, hurt, always recover. And now I obviously can't do a 4D plot for you, but what I can do is I'm just going to show you these three. And then if you're asking me about the fourth one, I'm going to say, well, it's just 1 minus the 3 that I am showing you. Okay, so now I'm going to have these 4 points like this. Okay, and so, you know, this point is the happy point where everyone is helped. This is the point where, unfortunately, everyone is of type hurt. This point back here, anyone want to tell me what's the point back there? Shout it out. Would that be?
Never recovered.
Yes, everyone is of type never recover, and this is the point where everyone is of type always recover. Okay, so now I can go and show you. This is why I couldn't go to full screen. Okay, so here is our, this is the simplex. Okay, helped, hurt, always recover. And now the information I get from my randomized experiment gives me two restrictions, right? Because I get to know because the proportion of people that recover in the control arm, that's equal to the proportion of people of type always recover plus hurt. And so, then I can add these. So here's one plane, right? This is, if I tell you the proportion of people that recover in the control arm, for example, supposing I tell you that the proportion recovering in the control arm is 0.272, then you will know that the sum of those two proportions is sum of always recover plus hurt is 0.272, and then you'll know that our distribution over these four types lies somewhere on this yellow plane. Okay? And then if I also told you, say, that the proportion of people recovering under treatment was 0.696, you would then know that we were that our population distribution over these four types lies somewhere on this blue plane. And now, because these two, because under a randomized experiment, the treatment group and the control group are both coming from the same population, we could then infer, what could we then infer? What would follow from that?
Are you asking us?
Yeah, I guess.
Any linear function of the outcomes under control and outcomes under treatment, or at least the average treatment effect.
Yeah, so basically the point is that the information from the control arm tells us that we're on this yellow plane. The information from the treatment arm tells us we're somewhere on the blue plane. So when we put those two pieces of information together, we've learned that that the population proportions must lie at the intersection of these two. Okay? So that's the information that we've gained from our randomized experiment. So the key point here is that we're not, even though we did a randomized experiment, we're not able in general to know the exact distribution over these four types. It could be anywhere along this line, but it's also the case that every one of these distributions along this line will have the same value for the average causal effect. Okay, you can sort of see that from middle school arithmetic, that if I'm telling you the sum of these of help plus always recover and the sum of hurt plus always recover, then when we take the difference between those two, that's help minus hurt. So it's not surprising that this, although we can't pin down exactly the distribution over these four types, all the possible distributions over these four types will share in common that they correspond to exactly the same value of the average causal effect, the difference between the proportion helped and hurt. Okay. Any questions about that before I go on?
Yeah, can you hear me? Oh, yep. Okay, great. So this is an interesting, like, geometric way of seeing this. I have two questions. The first is, I think I don't see it in the geometric picture that you have, but I believe that I can estimate any linear function, not just outcome minus, treatment under outcome minus treatment under, or outcome under treatment minus outcome under control. My first question is, what's the geometric way to see that? Is there some hyperplane going or thought, or what? Yeah, what's the geometric way to see that in the picture that you have here? And the second thing is, this relies a lot on binary outcomes. Is there a similar geometric thing that you have in your head for non-binary outcomes?
Yes. So going back to your first question, yeah. So I mean, I think if we look at the proof that was here, right, you can see that if you put in here, if you were to take the expectation of a linear combination of these two things, obviously we could go through, we could pull out those. So I don't necessarily have a immediate way to see that in terms of this picture. So I will also say this is specific here to binary outcomes. But yeah, my motivation for doing this is I want to be able to show you what happens when we deal with instrumental variables. And yes, as you can see, when we're thinking in terms of these potential outcomes, already even just with binary things, there are enough, the number of quantities, we have quite a lot of quantities to think about, and keeping things to binary allows us to visualize everything that is here. Any other questions?
Not from the room.
Okay, great. Okay. Yes.
On Zoom.
Question on Zoom.
You see it? Can you clarify the model for individual outcome probabilities in this framework?
Yes. So at the simplest level here, each individual is just of a certain type. So it's sort of, we could say it's like a Calvinist. It's almost a Calvinist view that there's just a big book, and written down in that book, sometimes called the full science table, just is the outcome. So essentially we have a distribution here because we might be thinking about these people as being in some large population, and then we're going to the people in our study are going to be randomly selected from that population. I'll come back to that point a little bit more, because there was also some questions about finite population inference, which I will also say a little bit about. Okay. But yeah, I think actually just to add a comment here, I think it's important to say the idea is the potential outcomes. We have a distribution over potential outcomes, and then the realized outcome is then a deterministic function of the treatment we decide to give someone and their potential outcomes.
Just another clarification question on Zoom. Are we thinking of random variable y as the outcome for a particular individual, or for a randomly chosen individual? What does it depend on?
Well, I think you can think about it either way. Before I choose the individual, it's a random. Before I choose an individual and decide what treatment to give them, then it's a random variable depending both on which individual I choose and depending on what treatment I decide to give to them. Okay. So there were some questions. Somebody sent me a message asking about how this connected to finite population inference. In finite population inference, there is a way of thinking about this framework where we just think about the set of people as fixed. So we think about the potential outcomes as constants that are specific to the people that are in, where we're only interested in a very specific population. Maybe it's an endangered species and there are only, 80 white rhinos left. So there's just a fixed population. There is no superpopulation that it's meaningful to talk about. And in that case, we would think about the potential outcomes as fixed, and then the randomness is arising from over hypothetical replications of our experiment, which individuals we're deciding to assign to treatment versus assign to control. Okay, so here in terms of the mathematical objects that we've got a distribution over potential outcomes, and then we've got our observed data, which under randomization, our observed data, this is the observed data in the control arm, observed data in the treatment arm, will be equal to the margins of this joint distribution. Okay, and we've seen, this is a pretty simple setup here. We just have these 4 types, and then we get to see these 2 margins of this particular 2x2 table. Okay? And what I've just shown you here was, given a particular observed distribution, we can go back and ask what's the set of all possible counterfactual distributions, what's the set of distributions over counterfactuals over these 4 types that are compatible with a particular observed distribution, and that corresponds to this line segment that we've got here. Okay, so that's randomized experiments from a potential outcome framework in this very simple setting. What about if I have What about if I have an observational study? Okay, so now I want us to think for a second like a legal scholar or a lawyer, basically. Okay, so for example, suppose that we've got this data. This is now not from a randomized experiment. This is from an observational study. And in this observational study, that some people got placebo, some people got drug, and then these are the outcomes. Now, supposing that you're a lawyer for the drug company, and you want to sort of come up with a story relating to this data that makes the drug look as good as possible. So we say here, well, what's the largest proportion of people of type HELP that we could have if I look at this data? Okay, so again, think like the drug company lawyer. These people here, they got the drug and they lived. Okay? So we know logically they either have to be of type HELP or of type always recover. But if we're going to be thinking like the lawyer for the drug company, what we're obviously going to say, well, all of these people are of type HELP, right? This is a miracle drug. They wouldn't still be here if they hadn't had our great drug. So all of these people we're going to claim are of type HELP. And likewise, these people here who are either helped or never recover, we're going to make the same claim. We're going to say that all of these people, it's tragedy. All of these people here, if only they'd had our drug, they'd all still be alive. These people over here, we're going to have to, it's a little harder, right? These people got our drug and they died. So what are we going to claim about them? What would be the natural thing to claim, thinking like a drug company lawyer?
They were doomed.
They were doomed, yeah. I mean, they got our miracle drug and they still died. So obviously, absolutely nothing we can do about them. They're all of type never recover. The people over here, they got the placebo and somehow they're still alive. So obviously these people are just, bulletproof. It's just, they're obviously completely indestructible. These are all of type always recover. Okay. So essentially, thinking if we're trying to make the drug look as good as possible, we're going to argue that the proportion of people of type helped is 0.65. It's these people plus these people. And we're going to claim that no one's hurt, right? Because remember, we argued that these people were doomed, they were type never recover, and these people are type always recover. So there's no one who's hurt. So if we're trying to make the drug look as good as possible, then the average causal effect here is 0.65, because 0.65% of people are helped and no one's hurt. Then, so that's our maximum value for the ACE. But now, if we turn it around, if we're now arguing that this is a very damaging, terrible drug, we're going to turn things around. We're going to now claim that all of these people are of type hurt. We're going to claim these people are of type never recover, and these people are of type always recover. So we'll end up with a minimum value of the average causal effect of minus 0.35. And so, so just to be clear, if you looked at this data, it has the same conditional distributions as the data set that we looked at before, which was when we looked at the randomized experiment where we could identify the average causal effect. So you can think about this as sort of a good news, bad news scenario. So before we saw any data, the possible range of values for the average causal effect was -1 to 1. So the good news is we've cut the range in half based on this observational study. The bad news is that the range of our bounds is still 1. And so that also means that in general, our bounds are always that will always hold. So our bounds will in general always include 0. So sort of in general, we can say this. So if we don't have randomization, what can we infer about this observed distribution? This is what we can infer. We can infer that the average causal effect lies between these two quantities, but these two quantities, the difference between these two will always be 1. Okay, what further information could we obtain? So here I'm going to ask a question that may seem a bit crazy at this point, because you might say, well, wait a second, you've already shown me that this, that we can't work out whether or not the average causal effect is greater than 0 or less than 0. Why are we caring about this? Why do you persist? But hopefully I'll motivate that in the second lecture. So here, suppose that we now do. Suppose that we now take. We could now think about our observed data as coming from a one-way table. Okay. So here, for example, the people who have x equals 0 and y equals 0, then, okay, so we get to know their potential outcome under x equals 0 under control. We know that's 0. We don't know their outcome under treatment. So our observed outcome over here is a sum of these two events. Here I've colored these to indicate this is the only thing that's changing on this row between this and this, right? It's that we don't know what would happen under treatment. Likewise, we can do the same for each one of these observed cells. So we could also rewrite this table like this, right? So I could say, so this is just the proportion of people who have x equals 0 and are of type never recover. This is a proportion of people who have x equals 0 and are of type helped, and so on. So I can rewrite the table like this. Okay, so why is that helpful? Well, it means that now we can ask the same question that we had before. So I'm going to give you an observed distribution, but now this is an observed distribution from an observational study. And we're going to think about what's the set of counterfactual distributions that are compatible with that observed data. Okay, so, and in particular, what we really care about is the distribution over those 4 types that map to a given observed distribution. Okay, so we're given the observed distribution xy. So if you like, we're given this margin. And what we really care about is the possible distributions over these 4 types: helped, hurt, always recover, never recover. Okay, so I'm going to claim, so first, for every proportion, these are proportions. So we get a free lower bound, no problem. They're all bounded below by 0. So I'm going to claim we can also get an upper bound. So I claim in particular that this quantity, that the proportion of people of type helped is at most probability x, the proportion of people with x equals 0 and y equals 0, plus the proportion of people with x equals 1 and y equals 1. Okay, so can anyone see a simple argument why that holds based on this table? So to make it concrete, supposing that 5% of the population is in the first row and 10% is in the bottom row, I'm claiming that proportion helped can be at most 15%. Why would that hold?
The 8 shoes are just in those 2 rows.
Yeah, exactly. The only people of type helped are on those rows. The other rows have no one of type helped. So the most that anyone that's of type helped either shows up on the first row or the 4th row. So the largest, I mean, it's possible that it's certainly possible proportion helped is less than this, but it can be no more than this. Okay? And we get bounds then for all of these 4 types. Can do the same thing, exactly the same logic. We get upper bounds on hurt, never recover, always recover. Okay. But we're not quite done yet, because we can also get bounds on the marginals. So for example, if I look at this guy, this is the proportion of people of type hurt plus always recover. That's the marginal probability for the outcome under x equals 0. That's 1. That's equal to the proportion of people of hurt plus always recover. So I'm going to claim that if we look at that, so if you ask me about proportion hurt plus always recover, this guy, that is lower bounded by this number. Okay, so I'm claiming that that the proportion of people of type who are of type hurt or of type always recover can be no less than this. You can probably see the argument for that is that, well, everyone in this row, everyone in that row is of type hurt or is of type always recover. So if I tell you that 20% of people are in that this probability is 20%, you know that the proportion of people of type hurt or always recover is at least 20%. Couldn't be any less than that because everyone in that row is of that type. So we get a lower bound, and we can also get an upper bound, because although there are some people of type hurt or always recover in rows 2, 3, and 4, in the first row there's no one of type hurt or always recover. So we've got an upper bound on this proportion. If I tell you this is, if I tell you this is 50%, then okay, 50% of the population is not of type hurt or always recover, so proportion of type hurt or always recover can be no greater than 1 minus 50% or 50%. Okay. So that now means that we've now got 6 pairs of parallel planes. So if you just give me a second, I will now show you. Hold on. Just a second. Just a moment. Just a second. Too many windows. All right. Sorry about this. My computer is being slow here. Okay, got it. Okay, let me take you through this. Give me a second. Okay, this is just visualizing what we've got here. So we had six pairs of bounds, 6 pairs of parallel planes. Okay, so just to put it all together, we've got upper and lower bounds on each of the joint probabilities, and we also have upper and lower bounds on the margins. Okay, so here's our simplex. Right, there's one plane that I'm not showing you here because if I put it in, we can't see anything. It's the one on the front. So those are the lower bounds that we see here. The purple ones are these lower bounds. I'm now going to show you what these bounds look like for the very simple case, just because it's easier to visualize, where all of these observed proportions are 0.25. Okay, so then we're then going to have, so we'll have upper and lower bounds for helped. Okay, so this is helped, this is the helped axis, this is the upper bound, this is the lower bound. We have upper and lower bounds on the hurt axis. This is the upper bound, this is the lower bound. We're going to have upper and lower bounds on always recover. This is the upper bound, lower bound is this plane. And we're going to also have upper and lower bounds for never recover. Right, this is the upper bound for never recover. The lower bound is this face of the simplex that I've taken off so we can see what's going on. Okay, so that's the first 4 sets of parallel planes. Then we've got 2 more, which are the bounds on the margins. So I'll show you those bounds. So here are the upper and lower bounds on always recover plus hurt. This is, these are like the planes that we saw before. This is always recover plus hurt. The upper bound, always recover plus hurt the lower bound, and we get the same thing for always recover plus helped. Okay, and so the set of possible distributions that we would have then corresponds to the little area that's inside here, which sort of here's one I prepared earlier. This was for the observational study data that we saw before. It's the same shape. It's a dodecahedron, but it's probably not what you think of when you think of a dodecahedron. This is a kind of less famous one. This is not the Platonic solid. This is its less famous cousin, the rhombic dodecahedron, where you can see some points have three edges meeting at a point, others have four. So it's not the one you think of, which has pentagons as faces. Okay, so I've got 2 minutes left here before coffee break, and I've got basically, I think about 2 slides left to go here, or 2 slides after which we can take a break. Okay, so this is the shape that we've now worked out. So what have we done? We started off with data from this observational study, and we've now taken that data and we've worked out that the possible distributions over these 4 types has to live inside this, this shape. Okay? And we could now, if we wanted to know about the average causal effect, we could then flip this shape over, essentially project out always recover and just look at helped and hurt. So this is just, all I'm doing is taking this shape and turning it over. So now this is help, this is hurt, and sort of always recover is going into the screen. And I can see this is the projection, and we have the same kind of not terribly exciting story where we've worked out that we have a distribution where proportion hurt is 0.35 and proportion helped is 0, and we've got another distribution where proportion helped is 0.65 and proportion hurt is 0. So our bounds on the average causal effect are going to straddle 0. So, you know, might not seem terribly helpful, but we're going to see actually that the work we've done here in working out what this set is going to turn out to be useful when we look at instrumental variables. Okay, so here's the summary. We've causal contrast compare the potential outcomes of the same units under different treatments, okay, conceptually across different possible worlds. For each observed data point, each unit, one outcome will be actual and the other will be counterfactual. So there are cases, you know, in psychology, there are some situations where you can do crossover designs where maybe you do get to see both potential outcomes, but the whole focus of causal inference in statistics is the situation where we have this fundamental problem of causal inference where we can only see one of them. A really great thing about this is it allows causation, which, you know, is something that people all the way back to Democritus thought was really interesting and curious and intriguing, and you can, you know, write popular books that sell very well. But what we've shown here, you may or may not realize, our little table reduced this to missing data, which is something that, you know, is of great interest to statisticians and to some other people, but it's not quite as exciting as causation. I don't think. Maybe there are probably some Greek philosophers that said, you know, if I could fill in that missing data, that would be great. But basically, the reduction in excitement when we go from causation to missing data, that to me that shows that there's conceptual progress. We've taken something that people think is mysterious and reduced it to something that people think is a little bit boring, perhaps mistakenly, but even so, we saw the ACEs identified if we have this independence. Randomization of treatment implies that. And then without independence, the ACE is not identified and cannot be bounded away from 0. And I'll stop there. Sorry for running over a little bit.
Thank you. There's one question in the Zoom that just came up. It's quite long. Maybe you could read it. So I'll read it. In the potential outcome framework, how do we understand the semantics of interventions? And epistemologically causal inference for so-called non-manipulable variables of individuals, gender, race, genetic ancestry, etc. The potential framework seems to take different stances from the graphical framework.
Yeah, so I'll take there are two basic comments on that. One is I sort of see that's a very good point, which is that the graphical framework, as it is often presented, I don't think it has to be presented like this, but as it is often presented, and certainly sort of in the paradigm examples, if you know, that Pearl talks about, there's this suggestion that we have a set of equations and that conceptually it's well defined to intervene on any given equation. I think it's an advantage of the potential outcome framework that basically researchers have to, you know, before you start off, you have to spend time thinking about, before you write down your model, you have to convince people that those potential outcome variables are well defined, and you have to sort of go through the trial by ordeal that anyone that starts talking about counterfactuals has to do. You have to sort of make an argument to say that that's a well-defined quantity that you're discussing. And I actually think that's right, because I think in a lot of applied and empirical work, that a lot of the hard work goes into very precisely trying to define what it is that you're talking about in terms of your intervention. So, you know, if we say something like, what's the effect of education on earnings? And then we say something like, oh, well, you know, let's have an intervention where we increase the number of years of education by 1. We could think about a lot of different ways that could be implemented. We could start people in school earlier. We could sort of prevent them from leaving school at the other end. We could drag people back to school after they've left. Those interventions that I think it's very reasonable to think will all lead to very different outcomes. And often a lot of the hard work that goes in testing hypotheses occurs in trying to come up with a precise formulation of what exactly is the intervention. And I think the potential outcome framework forces people, or at least should force people, to think carefully about what exactly are the potential outcomes they're talking about. Having said that, you know, there were papers that were written. One of the papers the paper that introduced the term Rubin causal model by Holland essentially said that there were, you know, that it would be impossible to think about, you know, that we couldn't possibly think about causal effects of gender or race because these were sort of intrinsic qualities of the unit, and we couldn't imagine what it would be to have for those to change. This falls into what I call the sort of the first law of empirical work, which is that whenever a philosopher says it's impossible to work something out, then almost certainly within a short period of time, some clever experimentalist will come up with a way whereby they can come up with an experiment that, you know, gets around, for practical purposes, gets around that particular objection. And I think exactly that happened with these objections, saying that we couldn't get effects of gender or race, that people very quickly did experiments where they you know, created populations of CVs and then randomly assigned names to them, or, you know, they did orchestra auditions where they suddenly said, why don't we just not have people audition for the part in the orchestra behind a curtain? Or, you know, Airbnb created fictitious customers that then asked whether they could stay in various hosts' houses, and then they could randomly assign. They were able to create populations, hypothetical populations, to determine whether or not people were being discriminated against. So, yes, of course, a statistician, you know, Paul Holland might still respond by saying, "Oh, but that's not truly changing the gender of the people that are in that are in our study." But I think for all practical purposes, it is getting at a causal effect. And so, yeah, so my answer is essentially that the answer is, I think it's a strength of the potential outcome framework that the bar for talking about interventions is set a bit higher, and that you can talk about causal effects for some interventions without feeling obligated to say that you know what it is to intervene on everything. I think that's a strength. On the other hand, I disagree with people who have said, that there's no way to get at certain causal effects, because I think clever experiments can always get at interesting aspects of causal effects for things, even if initially we think that they're not manipulable. That answer your question? Okay, great.
Let's take a break, 25 minutes. Thank you very much, Thomas, and we'll reconvene at 11 a.m. Pacific time.
Great.
Can I still ask, is Thomas in?
Thomas, should you take the microphone? That will probably work better.
Okay.
Hey, Thomas, can you still hear me here?
Yes.
Do you mind if I ask a question?
Certainly not, provided I possibly postpone answering if it looks like it's going to prevent me getting coffee.
Sure. Well, then I'll say it, and then do whatever you want.
Go ahead.
So my question is two parts. The first is like these bounds based on like knowing the different marginals here. Bounds on the joint, this like polytope that you have.
Yep.
My first question is, do people use this in like research papers? Because to me, it seems like it's like, if I just looked at like the volume, I mean, this is a weird measure to look at, but the volume didn't go down that much. So I'm wondering, is this something that is for us to understand in our heads, or do empiricists use this? And the second question I have is, it seems to heavily rely on binary outcomes, and I'm wondering if there's a meaningful extension to the real valued outcomes.
Okay, so two-part reply to that. So one part here is, so people often don't, so implicitly, yes. So essentially, these polytopes I'm going to show you, this is a bit of a plot spoiler, but essentially I'm going to show you that these polytopes underlie the bulky Pearl bounds for instruments, for computing bounds on average causal effects in instrumental variable setting. And I'll show that, in fact, this way of thinking about it lets you come up with bounds for more general situations than were originally considered by Pearl. And there is work that instrumental variable line of work has been extended also to think about has been extended further in other ways. I think you can extend to having, so it is the case that getting these bounds does depend on the response living in a bounded space. I think if the response is unbounded, you don't get interesting results. In terms of extensions, I think the thing which is hardest is to do this non-parametrically in the case where treatment is continuous. But so continuous but bounded response can be taken into account, can be done reasonably. Continuous unbounded response, I think, is certainly a limitation of this method.
Awesome. Thanks. I look forward to seeing the rest of it, and I'll let you get your coffee.
Excellent. Thank you.
Yep. Thanks.